byproduct of this reaction here, this alkene KMnO4 cold. Product would be what? Well, since we're on this page here, what's this going to give? KMnO4 cold, we will get the cis-diol. And so we could get OH, that structure plus what? It's an enantiomer, yeah? Cis-diol. Yeah? What if we did KMnO4 with heat and maybe acid? With oxidants are stronger when you have an acid. These metal oxidants. Basically, these lose oxygen. How do you make oxygen a better leaving group? Acid. The acid helps it do its thing. Oxidants with oxygen tend to be stronger oxidants in the presence of acid. That's why over here we used a little base and kept it cold. Okay. What if we kept hot? It's the same thing as ozonolysis, except aldehydes. Yeah? Yeah? Cleavage in the alkene, each becomes carbonyl. Why is this a carboxylic acid? Because the aldehyde does not survive with KMnO4. Big 3 will oxidize the aldehyde to the carboxylic acid, yeah? What if we treated this with ozone followed by zinc? Cleavage of alkene to give what? It'd be the same thing, except the aldehyde aldehyde survives if you use ozonolysis, right? But if you cleave with hot KMnO4, aldehydes will not survive. If you keep KMnO4 cold, it's only a partial oxidation. Carbon with no bonds to a more electronegative atom. Carbon now has one bond to a more electronegative atom. But over here, the carbon has two bonds to a more electronegative atom. And to achieve that, the carbon-carbon here got cleaved. So this is a more complete oxidation. This is sort of intermediate oxidation. What is another way to make this compound perhaps in better yield?
We can use that scary. Yeah, osmium.
Yes, next page, osmium tetroxide. That's a two-step reaction because the permanganate ester, the manganate ester is not stable. It will, with water, it will go directly to the cis-diol. The osmate ester is stable, and you have to come in with a magic step. What was magic for osmium tetroxide? Hydrogen peroxide or sodium bisulfite. Is it NaHSO3? Yeah. Or hydrogen peroxide. It may give better yield, but its osmium tetroxide is much more toxic than KMNO4. OSO4 is a neutral molecule. MnO4 is an anion. Yeah? K plus and all that's minus. Manganese is minus. Where do manganese and osmium sit in the periodic table? Manganese and osmium. They both have the same structure. The MnO4 and the OSO4 essentially the same structure. See, osmium is supposed to have one more electron than manganese. Essentially, to get that structure, manganese had to gain an electron to achieve to be that structure. And with that extra electron, the manganese with the extra electron is a minus. And since it's minus, you got to have a plus to go with it. So it's KNO4 or sodium, NaMnO4. But the most common with MnO4 is by far potassium. But OSO4 is actually a neutral molecule. And because of that, it's actually volatile. Physical properties, ionic, much less volatile. But the neutral osmium tetroxide is volatile, and thus it has vapor pressure, and you can breathe it, etc., smell it. But that's toxic getting into your body. Okay, a little review there of this of alkene oxidations, yeah?
Will we have to show the intermediate steps for some of these, or do we just need to know kind of our end products? Like the
Well, so a
main
lot of it
inputs
is just sort of memorization, you know,
Okay.
predictive product type stuff. We looked at mechanism for ozonolysis. That's probably the most important one. There's a problem or two related to that in the workbook,
Okay.
where you get some kind of interesting products based on maybe choice of solvent. Understanding the mechanism helps you address those problems like that in the workbook. Now, the alkene puzzle. Was it in the same handout? The very back, yeah? You remember I gave you that alkene puzzle in Organic 1? Remember that? But in Organic 1, when I gave it to you, I had three answers already filled in for you. Okay, you look back, okay. I'm giving you it here again, but I'm not giving you those three answers. Okay? A lot of this is your alkene review. Final exam's comprehensive. But the three I did not answer for you here are actually reactions which we're covering now. For example, which ones are we covering now as opposed to, right here, number 5. You see the ones that I starred? Well, that's the same I gave you in Organic 1. I said the ones I starred we're not covering, we'll cover in Organic 2. Well, guess what? We're covering them now. Okay? Yeah? What is this? Unfortunately, they made a typo, and it will be there for the rest of humanity. It's not a carboxylic acid, it should be a peroxy acid. And what does a peroxy acid do to an alkene? And the most common peroxy acid is MCPBA, metachloroperoxybenzoic acid. By the way, meta we'll learn in nomenclature of aromatics, ortho, meta, and para. Okay? What is this?
Grignards.
A Grignard reagent, yes. Was there another one that was starred?
Number 18.
18? On the left, yes, written over there. Look at there, O3, followed by dimethyl sulfide. Ozonolysis. Okay, so we've now covered these reactions here in Organic 2. Your other guys covered ozonolysis in organic 1. Did you see osmium or K-4? Any of the other stuff?
Yeah, we did both. We saw both.
You saw osmium? Okay. Did you look at mechanism, osmate ester?
No.
What type of magic step did you use? Okay, so there's some reactions. Again, the ones I started are the ones we're doing now. The other though is review. You don't necessarily need to be reviewing right now, but again, the final exam. So these are, this was published in the Journal of Chemical Education a while back, and it's kind of reactions that are introduced in organic chemistry. Alkene reactions. While we're here in this handout, look at a couple of applications. This is from organic synthesis. Top organic synthesis, collected volume. Organic synthesis is a annual serial. It may be monthly, but basically, and they produce procedures. Okay, it's not so research papers, but it's actual procedures. And these can be very useful for learning and seeing how things are done. Here's a ozonolysis of this alkene, and you see the alkene is cleaved against aldehyde and ketone, yeah? Okay. Now, that molecule then undergoes a second reaction, okay, an aldol reaction. An aldol reaction we'll cover near the end of this semester. So you should only kind of be looking for now, going from here to here. This is an exact procedure, tell you how it's done, how ozone is handled. It's a gas. Okay, so it's practical information on how such a reaction is actually done for those who are interested in such. The ozone is bubbled in as a gas, and it has to come out, and it goes to a Ki trap. The Ki trap does two things. First off, it quenches, it reacts with the iodide. Remember in lab last week we showed iodide can be oxidized to iodine, and hyperchlorite did that. Well, ozone is also an oxidant that will do that. And so it gives you an indication that there's an oxidant coming out when it turns purple. But this also destroys your ozone, because you don't want ozone just going out into the atmosphere. So you run into a Ki trap, and the ozone gets destroyed. I don't show the byproducts. This is probably just O2. And it's probably also water or something. I don't know what the fate is of the oxygen. And there's got to be some protons here, but it's also a way to sort of destroy the ozone as it's coming out of the reaction. This gets converted to that, and this gets converted to something else, so it's destroyed. That's called scrubbing the gas as it comes out. So iodide can scrub the ozone. So some practical information there. Over here is a synthesis of Zoloft. And let's look at what they're doing here. This reaction here they first make this cyclopropane. This is a reaction that we've never seen. It's an alkene. This gives a carbene. It's a higher level reaction, but the cyclopropane. From here, what are they doing? From here to here. This has become an ester, basically cleaving this here. oxidative cleavage, and this carbon, if you cleave that with ozone, this carbon would become what type of functional group? A carbonyl, but it would be a
Ketone?
an aldehyde, right? Okay. But what are they cleaving it with? What is B? KMNO4. They're also using sodium iodide. They're basically, that is sort of like heating with KMNO4. It's cleaving to the, not the aldehyde, but the carboxylic acid. So the aldehyde essentially gets oxidized. So the end result is carboxylic acid. That's after B. They then come back with C, and C is shown here, same thing as down there. Dimethyl sulfate, potassium carbonate, acetone. What are they doing in going from here to here? This is condensed, but there's the acid. They deprotonate with the carbonate, and then the carboxylate anion attacks a methyl on dimethyl sulfate, and the oxygen becomes methylated, and now they have what? Not a carboxylic acid, but a what? I think you guys are having trouble with condensed here, right? Carboxylic acid condensed, methyl ester condensed, right? There's the CO2H condensed, and then they convert this to what? The methyl ester. How? Carbonate deprotonates, right? And then dimethyl sulfate, right? These electrons attack the methyl, kick off that, yeah? Okay? And so C is where they come back. They just combine these two steps on their scheme. But first was an oxidative cleavage to the carboxylic acid, then they just came back and methylated the carboxylate. So that's an example of an alkene cleavage here in the synthesis of Zoloft. Yeah? Back over here. Question below over here. How would this transdiol be prepared? Because an alkene can be converted to a cis-diol. How would you get a transdiol? Did anybody come up with something on this one? Anybody?
What if you convert it to an epoxide and do SN1 conversion?
Yeah? Yes, if you go by an epoxide, convert, react this with MCPBA, and that would give us what? That there? Plus what? Plus what? Plus an antimer, yeah? The 2 bonds to the oxygen can be forward, or the 2 bonds to the oxygen can be back. Yep. The alkene has a face. It can attack the MCPBA from the front or from the back. Attack it from the front, then the oxygen does what? Back bonds, but it's all concerted. Okay. Now, what would you react that with?
An acid. With the protonate. Do you have to protonate your oxygen to make it a better leaving group? So
Do you always have to protonate the oxygen over oxides? Then when do you not have to protonate?
Strong.
If you're using a very strong nucleophile, you do not have to protonate the oxygen, like a Grignard, or we showed some. Two ways you could do this. We could convert this to this using sodium hydroxide aqueous. That would give that product. I'm sorry. I'm sorry. Down here I don't have the methyl group. I should have included the methyl. It's kind of they're kind of separate. I got a methyl there, but no methyl down here. You want to add a methyl down here? Okay, I think we can just add a methyl here. I think we got the right stereochemistry. Yes, I've got the right stereochemistry here. I was thinking maybe I needed to draw the enantiomer, but I'm good. We're good. Okay. So, react this with sodium hydroxide. Hydroxide is a strong enough nucleophile that it will do something. And by the way, since we're under basic conditions, you can't protonate the epoxide. You protonate things with strong acid. You don't have strong, everybody agree there's no strong acid here? Okay. So, remember this attack, top or bottom? Bottom. This attacks here and kicks the oxygen off. What do we get? Mechanistically, we get, well, it's going to be there's going to be an OH down here, but it will be back, right? Methyl is back. And what's here? O minus, yeah? And what do we need to get to the fountain? Just need an H, but what can supply the H? Yes, actually water can supply the H. And so these electrons take an H from water, these stay behind, that gives what? This, yeah? Transdiol. Plus what? What's reformed here? Yes, hydroxide reformed. So this is really, we're just reacting with water. It's really, this is reacting with water, but mechanistically this doesn't react with water. And the sodium hydroxide is what in this reaction? Yeah, the sodium hydroxide is just catalyst. Ultimately, a water molecule is consumed, and the sodium hydroxide catalyst is reformed. Why is sodium hydroxide needed? Right here, because only hydroxide will do this and open this up. Water is not strong enough. We need a strong nucleophile to open this up. But we could have did this another way. What's another way we could convert this epoxide to that? we need to react with water, but hopefully you got some room somewhere to get there. We could do this. Water, but use what catalyst instead? Non-hydroxide is catalyst, but what other catalyst could we use?
You have to have an
Acid, yes. What's your favorite acid? Yes. We could use that as catalyst. How would that act as catalyst? Well, how does any acid act as catalyst? Usually protonate something, right? Can I just protonate it without having to redraw that? So if we have acid, we can get there. But see, now water will attack that. And now we can have H2O. This is going to give us the enantiomer, I think. Where would it attack? Top or bottom? Top or bottom?
Wouldn't the leaving group be first?
Well, so I assume so that's a different question. Are we going to do chemistry top or bottom?
Top.
Top. Everybody agree? What was the rule I gave you that I want us to go by? If there's a tertiary site, yeah. Going to attack at the top. This is the case where, is it going to leave? What's going to be the stereochemical outcome of it? This is that funky business. It's going to be an SN1 with inversion. So it's going to add up here, but does this just open up? See, I don't know how to do it. If I do it SN2, it's going to look like SN2. If I do it, it's supposed to be SN1, but it's kind of both. Should I just show it as SN2? Because if it's SN2, we should be attacking down here. Let's substitute. If that just leaves, what do we get?
Tertiary carbocation.
This comes down here, just OH just opens up in the left one, correct? And then we're just left with a carbocation up here. That's trigonoplanar now, so I drew it planar. Then if the water attacked here, you would say, well, it should be racemic, but you actually get inversion. Why? Because this is very much, see, now that looks like a dashed bond instead of a bold bond here, and it's really supposed to be an IMF. So this is very hard to show. Basically, can I maybe just get the product? What are we going to get on this carbon? This is another erase. This is going to open up like this, right? The water's bonded up here, but it's going to come in backside. It's like, how does it come in backside? Okay, backside is going to be back. It's going to push the methyl forward. The oxygen has two H's. And however it gets on that carbon, it's like, it's going to be there because it's SN1, but it's inversion because it's got the crazy business of SN1 with inversion. Is that what we just did, SN1 with inversion? Okay. So what do we need to do to get final product? Now the final product is actually, this is going to be the enantiomer of it. Because this will be plus an enantiomer. This will give the enantiomer. How do we do it? Well, whatever gave up the H takes the H back, right? Okay. And the enantiomer will be what? Everything will be switched. Methyl's back, methyl's forward. OH is forward, OH back. OH back, you see how it's the enantiomer? this also gave an enantiomer, because there it is right there. And when OH attacks that, you also get the enantiomer. Everything up here has an enantiomer. Okay, so we could get the trans diol two different ways. Basically have an epoxide reacting with water. But you can't do pure water. You would either have to have sodium hydroxide catalyst. It acts as a catalyst by being denucleophile. Or you have to have an acid catalyst. And it acts by protonating the epoxide and making it more electrophilic. With the protonated epoxide, the weaker water will attack. And it's that strange mechanism. It's going to end up here, but it's inversion. It's SN1 with inversion. Crazy business. Question?
Yes. Which one would be favored?
Do what?
Which one would be favored? Like, which of the mechanisms would it use? Like.
Which of these? You can do either way you want. Two different ways. Ultimately, we're adding water to the epoxide in terms of stoichiometry. But we've got to have a catalyst. Because pure water doesn't react with an epoxide. You'd have to protonate it to get it to do regular, like we do with any alcohol or ether. Almost.
I was just wondering because of the rule that said if you have a tertiary carbocation, you should go that way. Like you should do SN1.
We did.
Or SN2. So I was just wondering, like, if you were to do this reaction in the lab, like, would you go SN1 because of that rule rather than SN2?
With the acid or with the base? Well, under basic conditions, the mechanism is always SN2, right? And we did. And in SN2, you attack the least sterically hindered site. Under acidic conditions, that's when we had a choice. And we said if you have a tertiary site, to go SN1. And that's what I did. That's why I did chemistry out there. But we have this convoluted stuff with epoxides, SN1 actually gives inversion. Why? Because when the leaving group leaves, it's really not a free carbocation. There's enough sort of IMF association here that it blocks one side. Because the leaving group hasn't totally left. And physics tells us that electrons are going to be attracted to a positive. So it's really not a free carbocation. So is it really SN1? It's a blend of SN1 and SN2. It's convoluted. Okay. It'll take me an hour to erase. Well, I got a sweet spot right here. Yay. Oh, not too bad. Okay. So a little review, yeah? And we can actually get transdiols ultimately via the epoxide, okay? Now, do you guys with Dr. A.J., do y'all react with epoxides in organic one? Because sometimes I think it might do that. I don't do it because we do enough in organic one as already. And so I've covered it here. Other questions? Did we finish everything here? I think there's one ozonolysis here. The ozonolysis question what was the starting material? Did someone get that one? Someone get this? Pretty straightforward, yeah? What does ozonolysis do? The two carbons of the alkene get cleaved. So if you go backwards, cleave to carbonyls. So guess what? That carbon and that carbon are going to come back together as the alkene. So alkene, this carbon over here has what? Two ethyls? And this carbon over here has what? A phenyl and an H. Is it okay if I don't draw that H in? There you go. How we doing? Do we have to worry about any stereochemistry over here? Is this alkene stereogenic?
No.
No, it's not. So it doesn't matter. I could have drawn the phenyl down to the same thing. Regardless of that, would it have mattered? If the alkene was stereogenic, should we have drawn it in E or Z?
Yes.
E or Z?
You said if it's stereogenic?
If it was stereogenic, should we have drawn E or Z? Do what? Yes, this alkene is not stereogenic. But if it was,
It would depend on the compound.
no, it would not, no, would not depend on the compound. Here, let's try another one. What if, let's take that one and let's take well, I think we can just do yeah, okay. What alkene would give these products? It's the same thing, I just took off a methyl group. It would be what? That there? Or that there? Which one? See, in this case, the alkene is stereogenic, and I showed both. Which one would we use? The answer is either. Either one will give these two products. Either.
Because you're splitting it, right?
Yeah.
So
You're
then
just
it
splitting.
can rotate and you can.
If you split this, what would you get? These two. If you split this, what do you get? Those two. My point is, if the alkene is stereogenic, either one is the same thing once you split it. It doesn't matter. But in the example I gave, the alkene is not stereogenic. You can choke the phenyl down, but that's the same exact alkene, right? Right? Review, right? What's the relationship between those two compounds there?
They're the same.
They're the same exact compounds, right? Okay, what's the relationship between this and that? It's the same hand. I just did that. Okay, that's the idea of stereogenic alkenes, right? Okay. All I'm trying to tell you is if your alkene is stereogenic, it don't matter. It depends on what the question said. What did this question say? Not much. If it says give an alkene that upon cleavage will give these two, then either one works. That's what I'm trying to say. But again, review, stereogenic. Everybody good with stereogenic alkenes? Okay, organic one. Okay. So what is the starting alkene? Did we cover everything in that handout? Anything there? Box size. Anything left in any of the handouts that we needed to look at?
Can you please do the synthesis starting with styrene?
Starting with what?
Styrene?
Styrene, which one would you like to do? You want to do the last one? Well, I don't know if we got time to do them all. About the last one. Main functional group here is a ketone. You know any way to make ketones? Actually, you know two ways. Tell me one way.
We could do BH3.
You said BH3?
Yeah. Did we do a?
BH3 is for antimercarbonic hydration of an alkene to give an alcohol.
Oh, sorry.
Hydroboration oxidation gives an alcohol from an alkene. We want to go back. That's how you make alcohols. How do you make ketones? Ozonolysis will give a ketone. The problem with that is, typically when you in synthesis, you want to go from small molecules to larger. Okay? Ozonolysis actually goes from a larger molecule. If you want to make this, if you want to make that ketone there, if you want to make it from this by an ozonolysis, you're actually taking a larger molecule and cleaving it to a smaller. So in terms of synthesis, it's not always the best. Now, I showed you one with Zoloft when they used essentially it. Okay. There's some cases when it is good. But in general, keep that in mind. Usually we want to go back to smaller molecules. And indeed, this has how many carbons total? 9. We're going back to something that only has 8. So, yes, ozonolysis is a way to make ketones. What's another way? Oxidation, yes. So this can go back to what? That here? If you had that alcohol, could you make that ketone?
Yes.
How would you do it? With what? And your favorite? You can use KMNO4. Now once we get to aromatics, we're going to have to be more careful about that. Okay? Yes. So now there is, how do you make this alcohol? Now we could do a hydroboration of some alkene. The problem is we need an extra carbon somehow eventually, because we're asked to start with a 2-carbon side chain, this has 3. Huh. Carbon-carbon OH. This is in the epoxide handout, right?
Yes, so we start with epoxides, right?
What could you envision here?
Grignard reagent.
We could go back to this epoxide, a 2-carbon side chain off carbon-carbon OH, and make this bond here, carbon-carbon OH. What would that methyl be? Yes. A methyl magnesium bromide or iodide, might be common iodide with the methyl iodide. Would these two react to give this? I'm going to draw 2 arrows because what do you have to have here to get the H on? H2O workup. Okay? Should, very standard reaction, right? And so now, how are you going to make the epoxide? Well, there we are. We're back to, we can see, this can go back to that, but at this point we just say, bam, we just react that with MCPBA. There you go. Styrene to the epoxide with the Grignard, and then this you can oxidize up to your carbonyl. How do you make alkyl chlorides? One way is conversion from an alcohol. React an alcohol with what? Maybe PCl3, SOCl2, if it's just maybe HCl. How do you make methyl ethers? Ultimately, those two can be made from the same type of alcohol, you just vary what Grignard you bring in. I mean, here you bring in an isopropyl carbon-carbon OH. If that was isopropyl and OH, could you convert the OH to the Cl? Or replace it with the Cl? Alcohols. Because once you get the alcohol, you can oxidize it, you can convert it to a chloride, or if you had an OH, could you go to the O-methyl? That's an ether synthesis, Williamson ether. Deprotonate, and then react with like methyl iodide. That's just varying. To get to those, you just vary the, instead of methyl, maybe you need an ethyl or an isopropyl Grignard. Very similar, it's just that the alcohol you then convert it to different things. Okay? We will have a quiz on Wednesday. It will include NMR. That warm-up page for the NMR has lots of good questions on it, okay? I sent you, you have a key to that, I think. Did I send the key to that out? Okay.
And you worked it in the videos as one of the last one.
I went over that warm-up page.
And they'll do it in the last video.
Okay. Have a good day, guys.